Hi, welcome to part 2 of the RL Fundamental series. In part 1 of this series, we talked about reinforcement learning, gave an introduction, and talked about a basic policy gradient algorithm, reinforce, which is used to, basically train a model to do complex actions like play a game, for example, in an environment. Today, we are going to be talking about actor-critic networks, which is an algorithm that extends on this idea and mitigates some of the challenges. But first of all, let's do a quick recap of how RL works and just see what are the challenges and why do we need like more advanced algorithms than the one we talked about in the first part. So in case you've missed the first part of this video, you could take a look at it. But I will try to like go over like much of the fundamentals in this video as possible, so you can just like quickly ramp up on that. Um, so the fundamental thing that RL does is just allow us have an AI agent, which could be some small neural network or something more complex like an LLM. So for example, you could think about your cloud code, your codex as an AI agent, right? And it takes actions in an environment where the environment could be a code base. It gets some reward, which could be maybe some test passing, and that's continue that loop continues where the environment returns like what's the next state of the environment and some reward, and you can take actions. So this is like how RL agents are trained, and we then like use like this sort of RL loop to like update it, where you basically have uh, this time step where a time step is basically any point in time in which the agent is acting. So you could, for example, when the agent is an environment state ST, like this state from the environment, like what does the world look like right now? We could use a neural network, also called like the policy here. In this policy pi, which is typically a neural network, and you sample from the range of actions available in that state, right? So you get action T. So you see state T, take action T, you take that action in the environment, and you get some reward at that time step, as well as a new state st plus one, which is the state that results from you taking the action, and then you update the agent and you repeat this loop until termination. So this gives you a very nice trajectory of you get a state, you take an action, you get a reward, and then that gives you a new state, you take a new action, you get a new reward, that continues. So this is the fundamental RL loop, right? And this is the same whether it's like you're training large language models or you're training, very simple models to like play some simple games. Of course, the actual implementation and lots of nuances differ significantly across all of this, but the fundamental idea is the same. And this is the way we typically like train this whole updating the agents. The way that typically works is we use what we call like reinforce, right? Which is what we talked a lot about in the previous video. So given a particular state st and you take an action at, you when you take an action in a state, you think about what is the total like discounted return you get in the long term, right? And that is like return GT, and that is basically like when I take this action in this state, as I take new actions in the future, by the end of the whole like trajectory, when you get to termination, what is the cumulative rewards I have gathered due to taking this action in this state? So again, the example that I like to use here is if you decide to take a particular job instead of another job, what does your career look like in maybe like 5 years time, right? So that's basically the concept of like GT, which is like your long-term return, while the immediate reward you get, maybe the immediate like salary increase, for example, is like think about it as RT, like that your immediate reward, long-term reward is GT. And what we would basically want to do is we want to train the policy pi, which is going to be, some neural network, probably an LLM. And we want to train it such that actions that lead to very high returns have their probabilities increased over time, and actions that lead to low returns have their probability decreased. And the way we do this is we basically, we compute the log probability of the action under the policy. So let's say we take an action T in state ST, right, using the policy pi. What we do is we look at, like, given the particular state, what's the probability of taking that action under this policy, right? It's like, for example, what's the probability of predicting this particular token in your LLM when you give it this input, where your state will be the context you feed into the LLM. Your A will be like the token you predict, and your pi theta is going to be your LLM parameterized by theta, right? Where theta is the parameters of your LLM or any neural network. I want to find the log probability of that. So once you obtain the log probability of the action that you took, what you then do is you multiply it by the GT. So for example, if the total return that you got in the long run by taking this action in this state is like really high, then you want to increase that probability, right? So you want to optimize your parameters in a direction that increases the probability. But if the returns you got is low, then you want to reduce the probability. And so in this case, think about it this way, that if the log prop is high and the return is low, then that will basically push our policy in a direction that reduces the log probability of the action. But even if your log prop is low, but your return is high, by multiplying it with a high return, you push it up, right? So that's basically, it's like just use the return to multiply the log probability, which is very neat and just works. And what we then do is minimize the sum of, like, cumulative returns, sum of like the return multiplied by the log prop over like the entire trajectory up until t, where t is determination, right? And why do we do minimization, right? Is that we gradient descent, we are always minimizing, but we want to climb up this hill, like we want to maximize this sum. And to the way you optimize the maximization problem in gradient descent is by just minimizing the negative, right, of the value. So in practice, we minimize the loss over like a batch of items, right? So this is what we do now. But there are a couple of interesting things to keep in mind. There are a few things here. So if you take a look at this time step, right, we talked about, we take the action, get the reward, we update the agents. It's not 100% accurate in the sense that we are not updating the agent, uh, right? We update the agent for every time step, but we don't update the agent at every time step. We only get the return GT after we've reached termination. So, which means when we take this action, we actually have to go all the way to termination before we can start updating the agents by then like traversing this trajectory in reverse order, which is like challenging in itself. That's introduced a number of problems we're going to talk about shortly. And so this is reinforced, right? This return, is the sum of like is the discounted sum of like future reward. So when I'm in state ST and I took action AT, then I, like, basically add up all returns that I get, taking new actions up from that state on, and like multiply that by a discounting term to like discount future returns because they are uncertain. There is what we call the variance problem, like with this, is that in a dynamic environment and even the most simple environment, you're not always guaranteed that when you take an action AT in a state ST, the returns you get in the future are going to be always good, right? I mean, it's the same with like life, basically, right? If you take an action, you could estimate with a high probability that, okay, maybe I'm going to end up in a really good place a couple of years from now by taking this action. But in reality, sometimes that will happen, sometimes it won't happen. So there is a variance, and you do not always know for sure what, after taking this action, what are the actions you are actually going to take in the future. So if we think about it this way, right? When training, what we go back to this, we take an action AT each time we are sampling a new action, right? And interestingly, you might take a good action here, and that sets you on a good trajectory. But then, as you during training, right? As you're sampling new actions, what might typically happen is that the actions you take in the future, right, might, are going to not always be very optimal, might lead you to a bad state, which means a lot of the times you take action 18 ST, you get good returns. A lot of the times, maybe you don't get good returns. And so this leads to like variance, right? Like a very, sometimes can lead to like a very high variance by which like taking the same action in the same state doesn't always lead to great outcomes. And that's because it depends on like, rewards from the future, right? And if you think about it this way, let's say we have an example where an agent took an action, up, right, and in state ST in, let's say you running your training and in iteration one, you got a return of plus 20. And next iteration, you observe ST again, you took action up, same action, and now you got a return of plus 2. Next iteration, you got a return of plus 5. This is like quite a bit of variance, and which makes it harder for you to actually promote staking up in ST, because sometimes you realize I get a high return by taking up in ST, so we increase the probability of up when it's state ST, and sometimes you don't get very high returns, and so sometimes the probability is not that great, right? So it makes the optimization really difficult just because of this variation in the kind of rewards that you're going to get as you primarily, of course, due to the fact that when you actually take the action, you do not update. You actually wait until termination, right, and then you compute the log prob multiplied by the returns based on total returns you get into the future, which depends on future actions that are themselves like sampled. And well, one of the interesting things to really understand about this, as we think about this whole variance problem, is the concept of state value function, right? So we have the state value, which defines like how good is it to be in a particular state. So let's imagine you are, in a state ST. Like, how good is this state to? How good is it to be in this state, irrespective of what actions I take in this state, right? So, just think about like, you know, let's say maybe you are driving, right, and you're trying to get to your destination, you know, quickly, right? And you find yourself in a state which is that you're on a road with no traffic, right? And that is a really good state, right? Irrespective of how fast you drive, of course, with like reason, right? Like, irrespective of like how slow or fast you drive, just being on a road that has no traffic just makes it's a very good state to be in, makes it easier for you to get to your destination. On the other hand, if you are on a road that has really, really bad traffic, irrespective of the actions that you take, it's a bad state to be in for your goal. So this is the whole concept of like state value, where the value of like in a particular state, and state value function basically kind of gives you that value. So it's the average return you expect to get, right, when you're in a particular state, right? And notably, it averages over the actions that the policy tends to take in that state. So if you, for example, find yourself in like a state, ST like maybe 4 different times, and you took like 3 different unique actions, let's say, while you are like on average, like what do you get, like when depending on like when you find yourself in that state, you take different actions, like on average, when we like maybe average over all the actions you took when you found yourself in those states, like what is the expected value, right, from that? So which is like why we have this expectation, which is like an average in time, like given like what's your average like return sort of when you find yourself in state ST. So that's the value function, right? Like how good is it to be in the state? There is what we call action value function, right? Which is basically what we've been talking about so far previously, which is like given you're in a particular state and you take an action A when you're in that state, how good is it to take that action in that state? Now, this is like one that we've talked about a lot already, which is like you find yourself in a state, you take an action, what is the total return you expect to get GT when you're in state ST and you took action A. All right, that's like the action value function. But the state value function is independent of the action, right? While the action value function is dependent on the action that you took. The advantage function is a new concept that we haven't mentioned before, and this is like at the heart of modern RL algorithms like PPO, GRPO, which is like, when you know how good it is to be in a particular state, right? And then we know like how good it is to take an action in a particular state. The advantage is basically the difference between the action value and the state value. That is like, okay, you let's think about it this way. You are on a road that is like has good maybe good traffic, and you could get to your destination in reasonable time because you're on a road that has good traffic, right? That's like your state value, right? Good traffic. Then one action you could possibly take in that is like maybe you are driving on the left lane. And let's imagine that on the left lane is slightly like this is a two-lane road, one direction. On the left lane, there's a bit of more traffic, like it's not as free as the right lane. On the left lane, you could think about the action you took of like going to the left lane and staying on the left lane as like one action, and the value of that action is like could be like worse. You might end up getting to your destination later than you should. But if you that on average, like compared to like just being like typical time you'll be expected to get to your destination being on that road, which is like not known to have much traffic. But if you on the maybe right lane, maybe the right lane is like much more free, it's easier to like get to your destination for some reason, then that has like an advantage over being on, and maybe like, or typically you get like faster. So the key is that your state value, right, gives you like sort of like average that you get being on this in this state, and then your action value gives you the value you get by taking a particular action in a particular state, and how much better that action gives you compared to the baseline that you expect in that state is the advantage, right? It's basically the value of taking action A in S and you subtract away the baseline, which is the value of that state itself. That's like that is your advantage, like how much better or worse is taking this action in this state compared to the expected return we get from like being in this state overall. So that gives you your advantage function A by SA, right? And so, advantage of the advantage function, pun intended, is just like you can, by subtracting a baseline, you reduce the variance of your policy gradient updates, right? Which makes learning more stable, right? Like just because the fact that you're subtracting any baseline at all, in this case, a baseline, which is the value, the state's value, right? It reduces the variance, means that each time the advantage that you get, right, is like much stable compared to like your total return, which can be like high variance. And an advantage helps you learn like what can I do better in this state, rather than just an absolute, or when I take this action in this state, I get this in the long run, right? Which you're not really sure, but you can be more certain about like doing this in this state is a better action than another action. Like, so even two actions can be bad. So maybe you took two different actions, they are both bad, and they lead to like even not so great long-term returns. But the advantage can really tell you this action is less bad than this action. In the same way, two actions can be good, and the advantage can easily tell you this action is better than this other action, which is also good, but not as great, right? So it's just a relative term that's like much easier to learn, of like doing something better than what you typically do in that state compared to like just an absolute return. So, which is why even if your total return is small, your advantage still helps you learn in a more stable manner, which because it's like it's improving the policy via relative comparison rather than an absolute term. And actor critic is like this line of RL algorithms that is, really designed to work this way by, using a neural network to estimate the value of a state. So this is the interesting bit about actor critic because, one interesting thing we talked about here is like you got an action and action value function. You got a state value function, and the state value function is like, oh, what's your expected return? But how do you estimate that? Like, how do you know how good it is to be in a particular state? And what actor critic basically does is you have one model that is like predicting what to do, and another model that is like learning how good it is to be in a particular state. And so you could then use a combination of that to like compute your advantage, which because you are estimating like how good it is to be in a particular state as you're learning, and then you can use that to compute your advantage. So that's basically what actor critic does, and we will like explain this more in detail. All right, so let's look at how actor critic works. What you typically do is you you sample an action, right? You take an action in the environment, you get a new state and you get a reward. You compute your advantage and you update your agent with the advantage. Now, I'm going to like still explain this more. But basically you replace updating your agent with a return by updating your agent with an advantage instead. And one of the key things is that you don't, because you're computing an advantage, and at this point, while I didn't show it here, I'll show it since pretty soon. You're also going to update your critic, right? But I'm going to show exactly how that works. One of the main differences is that at every single time step, you can update your agents, right? Like you can actually take, do right, gradient descent on your agent at every single time step because you don't need to wait until termination, right, to update your agent because you have the advantage, you have a critic estimating right at this step what the value is. You can immediately update your agent before you move to the next time step. While, in the typical example we showed before, you actually have to get all the way to termination before you can update. So that's like one big difference. And so let's look at like how the actor critic algorithm works, right? So you get state st, and then you sample the action from the policy pi, which gives you like action 80, and then you take a action 80 in environment and get the next state rt and st plus 1, and then so this is rt like the immediate reward you get. St plus 1 is the new state that results from you taking the action. Now the next thing you do is you estimate the value of ST using the critic model, like I said, just call the critic model omega here, while we use phi to denote, the policy model. So the critic model is another neural network, which basically gives you the value VST, right? Which is it takes in the state, the current state ST, and it gives you like what's the value, how good is it to be in this state. It's a prediction, right? It predicts how good it is in this state. And we also estimate the value of the next state, right? So in this case, these are two estimates, and we pass the next state, st plus 1, into the model, into the critic model, omega, which gives us again vst plus 1. And we compute what we call the TD error, which is what we use as the sort of the advantage here, as the new reward we got, RT, plus the next reward we expect to get, the reward in the next state, minus the current value of the state. Right, so this is interesting because we have our RT, which is the immediate reward. And then we have this, which is what is the, if we take this action, right, and we get this reward, what is the reward, what is the value of the next state that returns, right? Like what is the value of the next state we get into? So we add those together, and then we subtract, the current value of this state, right? We get what we call like the advantage, because the advantage is supposed to be, let's imagine the true value of VST should be both the reward we get immediately as well as like the value of the next state we get into. So if VST is like, if that is like the same, right, this would be like 0, which means like no advantage. It's just like what we would have gotten. But if the RT plus the value of the next state, which is also an estimate, multiplied by discounted by lambda, is actually higher than the value of the current state, the current value of the state, right? We know in that case that our action then is a good action, right? Is a better action that we would have typically taken, right? So what we this gives us basically that advantage is like basically we have the baseline VST, which is the value of the current state. We have the reward RT, which results from the action we took, and then we have the next state that we got into, which again is also dependent on the action we took. So this kind of gives us Q pi SA, which is like the action value, and then we subtract that from the state value. And what we then do is optimize this using policy gradient descent doing the log probability of that action in that state, multiplying it by the TD error, rather than which is also like the advantage here, rather than multiplying by the return. And the cool thing is that we can compute this in one step, like we don't have to wait on termination. Now, here comes the magic. It's like, how are we exactly training Omega to actually estimate the value of ST and the value of ST plus 1? We do that by optimizing the square of the TD error, right? So, because if you think about it really, really well, this TD error is also like in many ways we can think about it as like the difference between what the value of this state should be and like what our current estimate of the value of that state. So if we want to update our critic model to correctly predict the state next time, right, like we should, because like each now that we take maybe this new action and maybe we get like this particular value uh for the TD error, right? We know exactly now like what the difference is also between like our predicted current estimate for the value and like how good that state can be, and we use that to like update the critic model to like next time predict better the value of this state, right? How good is it to be in this state? And I did take this and actually use ChatGPT image gen to turn this into like a nicer diagram. And if you think about it, like the way this works, is that you just again have state ST, sample the action, you take the action, you get the reward at the next state, and then you compute your TD error, which is RT plus the like the discount factor multiplied by the value of the next state and subtract the value of the current state, and you update these two. You use the critic model to like estimate the VST and the VST plus 1, which is the value of the next state, and then you do your policy updates, right? You update the policy model with the standard, gradient, like, log probability multiplied by the TD error, not the return. And you also like optimize your critic by computing the square of the TD error. Right. So that's basically how the algorithm works. And we're going to understand it better by like looking actually at like the code, right? So this is like a single file implementation of the actor critic algorithm, including like defining the models, the training loop, basic testing. And what we have here is, first of all, we have the actor, which is like the A in A2C, right? And the actor model basically takes in a state of a particular dimension and outputs like the action probabilities, like, what's the probability of the next action like that you should take. And in addition, we have what we call the critic network. This should be critic. And the critic network basically just takes in the state similar to the actor. And what it outputs in this case is instead a single value representing the value of that state. Like how good is it to be in that state? So that is predicted. And the trainer is like very simple. I'm not going to like spend much on like this. This is just like us selecting like device, and if you're on Mac, use MPS. If you're on a GPU device, use CUDA. This is like basic. And then I'm on Mac, so it's like use MPS. And we have the state dimension, the dimension of the state, the action dimension, And then we initiate the policy model, which is the actor, as well as the critic model, which is the model we are going to be using to basically estimate our state value. So we're going to be training these two models in tandem, right? Where the actor model is exactly the model we are really interested in, and the critic model is the model that is helping this to learn by like itself it is learning to better estimate like the value of a state. And so one interesting thing here is that the critic needs to be trained at a faster learning rate than the policy, right? Because it needs to be good at estimating the value of the state in order to like help the policy line, right? So that is like like wanting to keep in mind here as to like set like learning rates or hyperparameters for both of this. And you want a good critic and then you want a good actor. Sometimes both of these are fused into one single network with like a single actor critic model that has like a policy heads and critic heads. But for simplicity, I've chosen to like divide them to two separate networks here to like make it easier to like make it more explicit, right? So training this uses like a very like straightforward training loop where we train over a number of episodes. And in each episode, what we basically do is that we have the actor yeah, we have like the states, yeah, and we take we create the state tensor, pass it to the policy model, predict the action probabilities. We get the predicted action by sampling from the action space and then the log probability of the sampled action. And we also compute the entropy of the action distribution just to help us, like, this is just a term we're going to use in the laws to prevent the policy from just collapsing to predicting a single value, right? So it's kind of like helps in the training as like a sort of regularization term. And we then take that, we also compute the value of that state. No, not that. At this point, at the initial step, the critic hasn't really learned anything. So the state value is entirely not going to be like very great, right? It is, and that's like there's a bias issue here, which is that the value we are using to update, we are using to compute our loss is itself from like a learned critic, right? And at the initial point, if it's going to be like nonsense because the critic will know nothing yet about the state value. But as we increase the training, as the training goes on, it's going to get better at estimating the state value, which in turn will make it easier for us to train our policy. So what we basically then do in this point is like we take the action, we get the next state and the reward, and we then compute the value of the next state, right? Using the critic, once we have the next state, we use that to compute the value of the next state because we're going to need to use this to compute the TDR. So as our equation was earlier, we do the reward plus gamma, which is the discounting factor, multiplied by the next state value minus state value. Note that both of these are estimated from the critic, which introduce a bias problem, which we are going to look into mitigating in the next video with like generalized advantage estimation, right? Which is just like based on the idea that rather than just doing this single step based on one single step, you could actually use like multiple steps into the future to like estimate the TD error, right? Rather than a single step. But that's out of scope for this video. So we'll then compute the actor loss by multiplying the log prob by the TD error, which is having as an advantage here, and then we subtract the entropy, multiplying that by a coefficient just as a regularization. We backward our actor loss and policy, and we update the policy optimizer. So the critic as well, we want to update the critic. So what we do is we recompute the state value of the current state, and then we compute the critic loss by basically doing reward plus gamma times next state minus state value, which is TD error raised to power 2, and then multiply that by 0.5, which is just to make the gradient more stable. And we backward the critic loss and take this step, right? And we change the state to be the next state, and we continue this loop. So at the end of this, we are going to basically have this nice dance of both the policy learning and the critic learning, and the Critic getting better at like helping the policy to learn and using the TD error to like update both, and where that represents an advantage, which is based on this, the reward plus the next state value minus the current state value, which is the baseline. So I already like ran this like previously, and then just like test it with this. So I'm going to like test this with this test loop. So I had this episode 162 as like the best performing episode during the training, and so if I run this a test of this, you're going to basically see something like this, where you have the catapult actually like going up and down for quite a while, and then if it's still going on, and now it's done, right? And so this is basically the whole point for like autocritic model, which is like we have a state, we sample an action, and then we use another model, which is being trained in tandem with the policy model to estimate the value of the current state and the next state, and then we use the difference between those plus the reward added to the next state value to compute an advantage, which we, in this case represent as a TD error, and we use that TD error to both do our policy gradients as well as to update the critic itself, so that the critic gets better at like helping the policy get better estimates to like learn from. So this is really the core of like actor critic, and this is a very powerful concept that extends to PPO, which we're going to also talk about in the next video, and even GRPO. It's just based on a much simpler way of like computing this advantage. GRPO uses a main rather than using like a value network of some sort. And this we're going to talk about those in the next video. In the meantime, if you got any questions, please feel free to like ask in the comments, shoot me an email, or reach me on Twitter. And for to get the notifications for next video and keep up with like these videos, please subscribe to my channel. And thanks a lot for listening. It's always really nice like hear your feedbacks, and like really fun to like make these videos. Thank you.